Hello, scientists. This is Dr. B, and we're looking at Activity 4, Sources, Sinks, and Feedbacks. We're on page 5. We've talked about carbon dioxide. We've talked about water vapor. Now we're going to combine the effects of carbon dioxide and water vapor and have a more complex model that will likely be more accurate. Usually the more pieces you have working in your model, if you can tweak it with some practice data, your model will be more accurate if you have more components to it. So we're adding carbon dioxide and water vapor in the same model. In the previous models, we used a temperature slider to set the temperature. Well, this helps us to figure out the relationships between temperature, carbon dioxide uptake by the ocean, and the amount of water vapor in the atmosphere. It's not very realistic. Nobody has a temperature slider for planet Earth. The model shows all of these relationships interacting with each other. Just as in real life, the only factor that you can control is the amount of CO2 emissions. Here, as humans on planet Earth, the only thing that we can control, we can't control the temperature of planet Earth, but we can control the amount of carbon dioxide we produce. We can't control volcanoes or some of the other sources of carbon dioxide, but we can control how many fossil fuels we burn. This model shows all of the relationships interacting with each other. Just as in real life, the only factor that you can control is the amount of CO2 emissions. Use the human emission slider to change the amount of carbon dioxide in the atmosphere. So we can lower the amount of emissions and run the model like that. Or I'm going to let the model run at that level for a while and see what happens to the air temperature. Even when we crank down the emissions, the air temperature isn't going to go down for a while because there's a lot of lag time for the planet to respond to the lower carbon dioxide level. The human emission slider controls how much carbon dioxide comes out of the factory. Now, obviously, there are lots of other sources of carbon dioxide, driving our cars, heating our homes. 0% means there are no human emissions. There are just all the other sources of carbon dioxide, like people breathing and animals breathing, bacteria breathing. 100% means that human emissions are the same as the year 2010. 200% means that human emissions are double the 2010 level. Now, this is an interesting development here. You'd think if we turn down the emissions, we'd turn down the air temperature, but that's not happening. And that's the result of all those positive feedback cycles that are going on. Once we heat the planet up and we start melting the ice caps, we get a lot of dark water exposed. We get a lot of deforestation and forest fires, adding more carbon dioxide. It keeps heating up the planet. And it takes a while for the planet to start to head in the other direction. Even if we take out all the human emissions, you can see it's going to take a while, decades, for the planet to respond and bring that air temperature down. Should we still try? Yes, because positive feedback cycles mean the more carbon dioxide we put out there, the worse it's going to get, exponentially worse. So even a little more carbon dioxide can cause a lot more damage. But on the other hand, taking a little carbon dioxide out can cause a lot less damage if we can turn those positive feedback cycles in the other direction. What does the human emission sliders do? Well, the human emission slider controls the emissions of what? Well, we learned that up here. Human emission slider controls how much carbon dioxide comes out of the factory. Obviously, there are many other sources. Basically, we got rid of the factory here, and the air temperature is coming down very slowly. So is water vapor in the atmosphere, and CO2 in the atmosphere, and CO2 in the ocean. How does the level of carbon dioxide affect the level of water vapor in the atmosphere? increase levels of carbon dioxide, do you think increase atmospheric water vapor or decrease it? Well, if we put more carbon dioxide in, what happens to the temperature of the air? And then what happens to the temperature of the water? And then what happens to the amount of water vapor? Remember, if we heat our water for noodles or make a steamy shower, we've got more water vapor. So let's turn up the emissions now. This is the ideal scenario where we took all the carbon created by humans out of the picture. Let's turn it way up. This is probably closer to what's really going to happen if we don't get our carbon dioxide under control here. We're starting to put carbon dioxide. Oh, there it is. Carbon dioxide in the atmosphere is taking off. Carbon dioxide in the ocean's taking off. Water vapor hasn't caught up yet because the temperature hasn't started to rise so much yet. There the water vapor goes. There's the carbon dioxide in the ocean going up. There's the air temperature going up. We don't have the ocean temperature, but we can guess that the ocean temperature is going up as well. And so when the ocean temperature goes up, the water gets warmer, it puts more water vapor into the atmosphere. So if the level of carbon dioxide goes up, the level of water vapor also goes up. How do we know that? Well, from our previous model, we know that if we heat up the ocean, we get more water vapor in the air. Just like when you heat up water for noodles, you get more water in your kitchen. It dissolved in the air of your kitchen. What happens to the temperature when the atmospheric CO2 level increases in this model? Well, we just cranked up the CO2. What happened to the air temperature? If you put more CO2 in play, that infrared radiation that's coming off the ocean, coming off the land, hits the carbon dioxide, or it can hit the water. Either one will vibrate more quickly and eventually cool down and then re-emit that infrared energy back towards Earth. So we know that both water and carbon dioxide are greenhouse gases that can absorb and re-emit infrared energy or heat. And so they keep the planet warmer. They make the blanket just a little bit thicker around planet Earth. How certain we are about our claim? Well, I'm pretty darn certain. We've looked at multiple models. With just CO2, carbon dioxide, and with just water vapor. And both those models showed a relationship between water vapor and temperature. Between water vapor, amount of CO2, and temperature. We know if we put more CO2 in, the air temperature heats up, the ocean temperature heats up. That puts more water vapor in the air, and that water vapor can also act as a greenhouse gas along with carbon dioxide. So we have our water molecules, we have our carbon dioxide molecules. They both can absorb infrared heat and re-emit it back towards planet Earth. So let's submit our answer here. Oh, I forgot to say. What happens to the temperature when the atmospheric CO2 level increases? Well, the temperature is going to increase. Hopefully you saw that in the graph and it's not a big surprise. HasBot's going to grade our answers. It's going to give me some specific feedback. Can you provide specific evidence from the model that shows how atmospheric CO2 affects temperature? So I'll leave that up to you to follow up on the feedback here from HasBot. I only got a 2 on my certainty rating here because I probably didn't talk enough about the limitations of the model. I talked about the value of the model we looked at before, but we need to talk about the limitations of this model. There are no ice caps, there's no methane, that's another important greenhouse gas. It's missing some components, so even though it's got more components, it's still not perfect. It's still pretty simple. So what we saw in the last model is called positive feedback. When there's a change in the system, the change gets amplified by further changes. So if you increase carbon dioxide, the planet gets hotter and you get more water vapor too. So changing one thing, increasing one thing, increases another thing and makes the problem even worse. That's a positive feedback cycle. Like melting snow in your backyard. If there's a big dark patch in your backyard, that patch gets, because it's darker and it absorbs heat better. Let's say you have some brown grass, like we do here in March in Minnesota. That absorbs heat and melts the snow. And that, when the snow melts, that brown patch in your backyard gets bigger. And that warms up faster than the snow, so it melts more snow around it. And then the patch gets even bigger. And so when you have a bigger patch of brown grass, that gets warmer and melts even more snow and makes the patch bigger. A bigger patch of warm ground melts even more snow. And that's a positive feedback cycle. It's great when you want it to be spring here in Minnesota, but if you're melting polar ice caps, which are the planet's air conditioning, it's not so great. So one example of positive feedback is studying to get good grades in high school. When you study hard, you get better grades. The better grades motivates you to study more, and your grades get even better, and you get on the good student track. It can work the other way though too. When you start to fail, you give up and you don't do your work anymore. So try to get on the positive feedback cycle on the way up instead of the way down. Describe a positive feedback cycle that affects Earth's temperature. Well, one example is sea ice melting. When sea ice melts, there's nice dark blue water that absorbs heat. Hot water melts more ice, making more sea available, more water, dark water available to absorb heat, which melts more ice, which makes more dark water, which melts more ice, which makes more dark water available to absorb heat, which melts more ice. That's a positive feedback cycle. So far, the models have only been showing increasing temperature, but obviously, since Earth has had ice ages in the past, temperatures don't always increase. What kinds of things to decrease Earth's temperature? Well, there was a year called the year without summer, and that happened after a volcano put a lot of dust all over the atmosphere, and it shaded the sun from heating the entire planet. And that was a positive feedback cycle. Once the planet got shaded, it cooled down, and then it just continued to cool because it couldn't get any more sun. And all of Europe didn't have summer, and a lot of people had difficulty growing crops. So when Mount Tambora erupted in 1860, all across Europe, it shaded the sun a lot because of all the volcanic dust. they had a lot of trouble growing crops because without sunlight, plants can't photosynthesize and grow. And then they couldn't feed all of the people because they needed to grow things to feed people. And a lot of people starved. So dust in the atmosphere can decrease Earth's temperature. There are other things. We look at them. They're white and fluffy and make interesting shapes that also shade the sun and are an interesting part of climate models because they're difficult to predict, and it's difficult sometimes to figure out if they're going to reflect more sunlight and cool us off or hold in more heat and heat us up. Those are clouds. So clouds can also decrease Earth's temperature, but sometimes they can increase Earth's temperature. Because when there are clouds in the sky, they act like a blanket. And they have this nice fluffy blanket. And winter nights in cold places, you know that it's going to be warmer if it's a cloudy night because the Earth radiating heat will go into the clouds and be re-emitted back down to Earth here. But the clouds also, if this is a cloud, reflect sunlight, so some of the light from the sun can't get to the Earth and heat up Earth. So we'll talk more about clouds in Activity 5. Right now, you want to show all answers. You want to find the little square with the arrow. You want to click on that. There's a little tiny version of options that'll come up on your iPad in a little menu. Click that options, click PDF, click back out, and click Notability. So square, options, PDF, and Notability. That's how you hand in your assignment. Thank you so much for watching. I'll see you in Activity 5. This is Dr. B signing off.